Hey, welcome guys. Yeah, so today let's keep talking about uniform convergence. Yeah, so in the previous video, I just mentioned that the sequence of function has a various bad property, like you cannot the double series is a troublemaker, maybe a troublemaker. And if even though if your Fn is continuous and Fn converge pointwisely to F, then Fn may not be continuous. Also, the differentiation may not be exchanged with the limit, and the integral cannot may not be exchanged with the limit. Right. So this looks like everything you expect it to work will not work. Okay. Okay, so that's why mathematicians have come up with the idea called uniform convergence, and the uniform convergence somehow like become the key idea to rescue all these problems. I mean, at least partially rescue. Okay, so hope you guys subscribe to my channel. So in this video, let's given a definition of uniform convergence, and talking about yeah. So yeah, let's maybe just talking about definition. At the various property, and then the next video we talk about and we will have the video. I think I will present 3 videos to solve all these 4 problems. Okay. Okay, so our settings this. Okay, so definition. If we have a sequence of function, let's say f of n from 1 to 2, So uniform converges on E. So set is E, right? That means that for all epsilon greater than 0, there exists n, right? So this n depends on epsilon, okay? Such that when n greater than n epsilon, let's say fn minus f of x. So f of x. So you need to assume that fn already converge pointwisely, okay? And the convergence function is called f of x, fn minus f of x less than epsilon for all x. So this is very, very important for all x belongs to E. So this problem, this idea is that given an epsilon greater than 0, you can find a universal n, universal large n, such that every function greater than n, and every point. So this is usual. So suppose you fix x, right? So if you choose x, then let's just say that f of n converge f of x for fixed x. But uniform convergence means that every x behave the same in this sense. Okay, so yeah, this is called a uniform convergence. Okay, so these for all x are all the most important word. Okay, so obviously that the uniform convergence will imply the piecewise convergence, right? Because if you forget about for all x, then it becomes piecewise. Okay, then you can define f of n of x to be as n of x, right? So let's say you go from, let's say m from 1 to n, and you can ask whether this guy become this, right? So this is, you can also talking about the series, some summation of this series, whether it's a uniform convergence or not, right? So basically you fix n, and you can define as n of x, and you can check this. Okay, so theory. So let's say this Fn, you have a Fn uniformly convergence. So uniform convergence on E. If only for epsilon greater than 0, there exists n such that when m greater or equal to n, and for all x belongs to E, we have Fn of x minus Fn m of x less than epsilon. Okay, so this is like a Cauchy property, right? And I forgot to say that in all of my video, this E should be viewed as a subset of the Euclidean, Euclidean space. Okay. Okay, so the proof. I think the proof. I think this. Let's see. Just give a proof, right? So the proof. I think these directions probably simple, right? Because I can write Fn minus Fm as a f of n minus f plus f minus f of m, right? So we can use the previous property to bound these two, right? So this direction is trivial. And conversely, there's since I already said that I in Rn, right? So I can use the property of the Cauchy, right? So Cauchy. Okay, so now this guy is a Cauchy sequence, right? For each guy, for each x, right? So obviously that Fn will converge piecewisely. But actually, this process is for all x, right? So I can easily get that Fn H converge uniform. Right, so the key idea is that you use Cauchy. Okay. Let's say theorem. So let's say we have this. Okay, so this just say that piecewisely, right? Piecewisely. And then let's define M of n to be sup x belongs to E. Right, so I can take f of n of x minus f of x. Then Fn converge uniformly on F if and only if. So this property is very powerful to get you to give you an answer when is the guy when is your sequence of functions converge uniform. Otherwise, usually it's not easy to determine. So let's say M is this if and only if this Mn goes to 0 as goes to infinity with a proof. I think let's see. I think these directions is simple, right? Because now you can see that this guy, right? This Fn minus F is bounded by this Mn, right? So in your definition, you have for all x, right? But in this case, you don't care about for all x because this is a constant, right? So you can use the definition. If Mn goes to 0, then you can use the property of the convergence of Mn to bound this Fn minus F, right? So these directions is trivial, okay? And these directions, Fn converge uniformly. These directions may little bit tricky, right? But I think it's, yeah. So let's do as exercise. Yeah, it's not difficult. You can do this. Okay. Okay. So Curry or theorem. Let's say now theorem. This theorem is also somehow like the same as this, right? So suppose you have a sequence of function f of n, and let's say Fn is less or equal to Mn. So this is usually called, I guess, is the so-called Weierstrass M test. So basically, if your every function f of n of x is bounded by some Mn, and then sigma Fn converge uniformly if and only if summation of Nn converge. Okay, so this is as the previous one, right? So you can basically just change this as a summation. Okay, so the proof is just simple, so omit it. So similar as the previous, okay? And you can just, I guess you can just, let me just write down the key step, right? Key step is that you use the partial sum. Right, and you know this ML guy is a Cauchy, right? So actually you can control this to be less epsilon, then you control E, the Cauchy term, and which you use this definition and you solve this, okay? Okay, so let's prove the theorem that I plan to prove. Okay, so this theorem is the first one which solved the first problem called the uniform convergence and continuity. Okay, so let's say f of n converges to f uniformly, and on some metric space E, and then let x be a limit point of E, so S be a limit point of E. So limit point means that I hope you guys do not forget about this, right? So limit point means that whatever open neighborhood x you choose, there's always infinite points which is not the same as x and the intersection with E. Okay. And then let's suppose, right? Suppose that f of suppose it's limit point, right? So suppose this is the suppose. Suppose limit t goes to x, f of nt become a n, right? For all, let's say n from 1 to 2. We keep going. So you fix x, right? And then you ask whether you ask the limit t belongs to x, and then suppose this limit always exists. Okay. Then and converge. Not only that, I can write the limit of an is n goes to infinity. An will become limit t goes to x f of t. Okay, so basically this theorem just say that you can write everything to be limit t belongs to x, right? F of t. What is f of t, right? F of t is basically the limit. So let me just write as this, right? And take the n goes to infinity is the same as you exchange the limit, right? So t belongs to x, n goes to infinity, f of n of t, right? So this guy is an, so this is this term, and this is this term. Okay, so that means you can change the discrete n to infinity with the t belongs to x, and the limit t belongs to x to n choose to infinity. Okay, so this is the theorem. So theorem says that if fn converge uniformly, then basically the limit can exchange with the discrete n. Okay, so let's just write down the corollary, and then we go to the proof. Okay, so the corollary says that what? So if you have a sequence of sequence of a function, and each f of n is continuous, and the fn converge uniformly on to f, then obviously the f is continuous. Okay, by the previous by this theorem, right? Because you can exchange the limits and the n, right? So yeah, so you want to ask about t belongs to x for f of t, right? But you can exchange it with n, right? So you can go to n, and you ask about so you can go to the, for each t belongs to x, you ask f of n of t, then you n goes to infinity, right? And obviously that you can see that since each of them is continuous, so this guy will be continuous. Okay, right? Because so each of fn of t is continuous, right? So this guy will be, since continuous, right? So f of n of x will just be f of x, right? So sure, you get exactly the continuous. Okay, let's go to a proof. Okay, so proof, basically let's prove this theorem. Okay, yeah, so this is an analysis topic, right? So you just need to bound something and try your best to bound something. Okay, so all I need to do is what? All I need to do is to bound this f of, right? So our goal is to prove limit n goes to infinity a is by this, right? So my goal is to bound f of t minus what? Minus this limit, right? So let's say right, a as the limit n goes to infinity an. So my goal is to bound f of t minus a, right? Because I want to prove that when t approach x, f of t will become this, right? So I just bound this. Okay, and to try your best, you need to, I guess this is very simple, right? You write it as three terms. Let's say f of t and plus f of n of t minus an, and plus an minus a. Okay, and I want to show that these three guys can be bounded, can be arbitrarily small as n goes to infinity. Okay, so let's write down what we have. So by definition, this guy can be bounded, right? Because my definition is this. Right, so this guy can be bounded, let's say epsilon divided by 3. Actually, who cares? You just need to bound this by epsilon, right? How about this guy? And this guy, okay. So how about this guy? This guy says f of nt minus an, right? Okay, so let's see. So by definition is this, right? So when t goes to x, f of t equals to an. Okay, so this is okay. So right, so you can, let's see. Yeah, so we need to bound these two terms. So somehow like we need to use different properties to bound this. So let's see, let's see these 1 and 2. Okay. So for the first term, this is bounded by what? By the uniform convergence, right? By definition, my f of n is a uniform convergence to f, right? So for all x, for t, I can bound this guy, right? I can bound this guy by epsilon divided by 3. Okay. And then we already bound this guy, right? So the remaining is these two. So the first one is uniform. Let's say this is third. So third is by definition. How about 2? Okay. Right. So we need to bound this term. Okay. Okay. So let's see how to bound this f of n of t minus a. Let me see what's going on. Okay. So this f of n of t to be an as t approach to x, right? So my definition should be, so I can choose what? So by definition, I can choose t goes to x. So I can choose a distance which is very close, right? T approach to x. So I can choose the distance with tx very small, right? So I can bound these terms by epsilon, right? By 3 over epsilon, right? So you can combine the 1 and 2 and 3. Yeah, so these guys are actually by definition. So you can see that actually the uniform convergence, the uniform convergence just tries to bound this guy. Okay, so by 1, 2, 3, then you get this. Okay, so you prove that this is the same. Okay, so you prove our results. Okay, so yeah, I think that's enough. In the next time, we talking about some results and we prove the uniform convergence and the integration. Yeah, so in the beginning, that maybe you think that the uniform convergence is very abstract, right? But if you go see the proof, then you can see the uniform convergence just try to bound these terms. So the proof is not difficult. Okay, and it's very interesting. Yeah, just this simple modification idea can give you what you want. Okay, so see you guys in next videos. Bye bye.